All right, hello everybody. I'm here playing around with Desmos's 3D grapher, and I want to try to find the equation of a plane that passes through three given points, and we'll try to find it in two different ways and demonstrate what each way tells us about the plane. And so let's just make up a couple points. Let's go 2, 3, 7. What about -3, 0, 5? And let's go with 1, 1, 2. Why not? All right, so we can see some of that. I think I need to zoom out a little bit to see the red dot. There we go. So we got three dots in space, and we're trying to find the plane that connects those three dots. Okay? So the first method is to come up with the direction vectors between the different points. And so we'll just call this one A, B, and C. So direction vector AB is going from A to B, so it goes down 5, it goes down 3, and it goes down 2. Direction vector AC, or I could have done BC, goes from A to C, so it goes down 1, down 2, and down 5. Maybe I should have gone the other direction so I'd have positive numbers instead of negative. Okay, but here we are. So here is one equation of the plane that passes through those 3 points. Let's write it maybe over here in the top right corner. The collection of vectors in the plane are always equal to any vector in the plane plus a constant multiple of one direction vector plus a different constant multiple of a different direction vector. And I kind of screwed up a tiny bit. This should just be the letter U for the vector, one vector that moves in the direction of the plane, one of the basis vectors, and V is the other one. So our specific vectors here, any point in the plane, I'll just use A, plus lambda times one of our direction vectors, -5, -3, -2, plus mu times another direction vector, -1, -2, and -5. Now let's see, I'm not super familiar with the format here. Let's see if I'm able to type that in. Let's see, what is it now in R? Let's see if I can do this. R equals 2, 3, 7 plus lambda. Let's see if I can make this work. Let's just use different parameters. Let's use like K times -5, -3, -2, and plus T. Okay, let's see what happens here. Okay, let me try something else here. I'm going to add an expression. All right, I'm going to pause for a second and figure out how to get this plane equation to work. Okay, so I'm not immediately seeing how to graph it in the vector format. So that's okay. We'll switch it to our Cartesian format and then it should work out. So anyway, to get it into the vector format, I write the three different parametric equations by just reading the top row, the middle row, and the bottom row. And then trying to eliminate them. What I see right off the bat I could do is I could go 2x minus y, because if I go 2x, I'm going to have two lambdas, or two mu's, and minus y would get rid of that. So if I do 2x minus y, I'm going 2 times 2 minus 3 is 1. 2 times -5 is -10. Minus -3 is -7. And then the lambdas are eliminated. Or the mu's are eliminated. What I'm going to do next is eliminate the mu's between x and z. If I go 5x, and then I subtract z, I'm going to have 5 times 2 minus 7 is 3. I'm going to have, excuse me, 5 times negative 5 lambda minus negative 2 lambda. So 5 times negative 5 makes negative 25, minus negative 2 makes negative 23 lambda, and then the mu's cancel out again. Now the numbers get a little nasty here, but you can multiply this top equation by 23 and multiply this bottom equation by 7 and then subtract them, and you will get rid of all of your lambdas. So now 23 times 2x makes 46x. 23 times y is 23y. And then I'll do the 7 times 5 is 35, and I'm subtracting that. So minus 35x. 7 times z is negative 7z, and I'm subtracting that, so that's a double negative, so plus 7z. And then on the right-hand side, I have 23 times 1 minus 3 times 7, and then my lambdas cancel out. Even though I don't know off the top of my head what 23 times 7 is, I know they cancel out. So now I have my Cartesian equation looking like 11x minus 23y plus 7z equals 2. And hopefully I did that right. And when I type it in, I should see a beautiful plane that goes through all 3 points. Let's check. And you can see for yourself that those 3 points lie inside of the plane. There is another way to find that equation that I just want to go over briefly. So instead of doing this method of using the 2 direction vectors, stop spinning. That's funny, it has like a momentum to it. Okay, instead of using that way, I can find the cross product of these 2 vectors right there. And I think that there's a way to do that in here, but I'll just do it by hand. So the cross product, AB crossed with AC, just look at your formula. AB crossed with AC is, sometimes I try to do it off the top of my head, other times I don't feel like doing that. So we're doing the second component times the third component. So that would be a new vector that goes negative 3 times negative 5 minus negative 2 times negative 2. And then the next line is V3W1, V1W3. So negative 2 times negative 1 minus negative 5 times negative 5. The last row is V1W2 minus V2, which is negative 3 times W1. All right, so hopefully I did that right. So we have 15 minus 4 gives me 11. 2 minus 25 gives me negative 23. 10 minus 3 gives me 7. Those numbers should be familiar. Those 3 numbers are the same coefficients that we just got before. We know also that the normal vector, you get a normal vector when you do the cross product. And we know that the normal vector multiplied by a vector in the plane minus a point in the plane has to equal 0, because the normal vector is perpendicular to all vectors in the plane. So I should be able to do 11, negative 23, 7, dotted, this should be a dot product, dotted with x, y, z, minus my point A, minus 2, minus 3, minus 7, to equal 0. Doing the dot product and distributing gives me this. 23 times 3 is 69. 7z minus 49 equals 0. The only last thing to check is we have negative 22 and 69 and negative 49, and that equals negative 2. So we have 11x minus 23y plus 7z minus 2 equals 0, which is equivalent to the other one. The other reason that I wanted to show this, though, is that the coefficients of the plane are the same as the normal vector. I thought that that would show me. Interesting. Let's try this. 0, 0, 0, 11, negative 23, 7. Okay, there we go. So I had to put a comma in between. And after all that work, we can see that that normal vector is perpendicular to the plane. Normal vector is perpendicular to the plane. And that was the whole point. All right, thanks for watching and bearing with my inexperience with Desmos 3D. Ask questions.